So Hoeffding analyzed this test in 1965, and he showed that the probability of false alarm misdetection has this approximation. So basically, the probability of error will decay exponentially fast with respect to the number of samples. Okay, and you also have the estimate on the order of error. Okay, so if your number of samples is increasing, then this term will dominate. And you can turn this around and define the error exponent, which basically look at the log of probability of false alarm and normalize by n and take the limit. Right? So this is basically the error exponent. So what error exponent tells you is basically the leading behavior, the first term, in how fast the error decays with number of samples. Okay. Any questions on error exponent? Okay. And if you look at error exponent, then you can show that Hoeffding shows that this test is actually optimal. So look at any test whose error exponent on probability of false alarm is bigger than the Hoeffding test, then its probability of error exponent on misdetection is actually smaller. It's no larger. Of course, you want a larger error exponent. Okay? So basically, we can say that Hoeffding test is asymptotically optimal in the criterion of error exponent. So that's a complete theoretical picture, but let's look at how this test performs numerically. So let me plot here on x-axis is number of samples. Okay, and the y-axis is probability of false alarm. Let me fix the threshold so that I can look at probability of false alarm alone. And it's plotted in the log scale. So remember, the theory tells us the probability of false alarm will decay exponentially fast with respect to number of samples. Okay, so if plot is a straight line. Now let me do some numerical experiment and look at what's the actual probability of false alarm. So let me start with a case on a uniform distribution on an alphabet of size 5, and you can see the slope is approximately really good by the error exponent approximation. But let's increase the number of size of alphabet to 10 or to 20. And you'll see that the slope for a small number of samples, the approximation is poor. Of course, if you look at the infinite number of samples, eventually you'll get the slope right. Okay? The thing that is, if you look at the number of samples that's comparable to the size of alphabet, the error exponent is telling the wrong picture. So we can say the error exponent is poor for large M. So what's really happening is that in this setting, this error exponent definition doesn't quantify well the impact of large alphabet. Okay? And that's the answer we try to answer. So what kind of analysis you can do so they can understand the impact of size of alphabet well. One way you can look at, recall this is the error exponent approximation, which only gives you a leading term of the probability of error. But you can look at the finite approximations to it. So one way you can do Behavior type of analysis. Basically, you have one additional term that's in front of the exponential decay, which is polynomial in number of samples, but that polynomial will increase with the size of alphabet. Of course, your error here, error term here is smaller. Okay? So this is one way to look at the problem that you can see that if you have a large alphabet, your test is going to suffer. Or you can look at central limit theorem analysis. So you can look at, remember the Hoeffding test is basically compare a certain test statistic to the threshold. And if you look at variance of that test statistic, it's actually proportional to the size of alphabet. Okay? Therefore, you have a larger alphabet, then your variance is larger, you have a larger error. And of course, you can do variance reduction using features, basically select subset of features. And that's what we looked at before in terms of mismatch test. But the limitation of above analysis is, first, if you look at approximation, how good it predicts for n much smaller than alphabet size, it's not very good. Second, it doesn't tell us what's the optimal, whether a test is optimal or not. Okay, you can analyze a certain test, but you don't know what's the best you can do. And in this talk, I'm going to follow a different asymptotic setting. And it comes from it's one kind of high-dimensional model. So remember, we have two quantities. First, we have numbers of observations. Second, we have Hoeffding size m. Okay. In previous Hoeffding analysis, we fix m. But in this case, let us make them grow simultaneously to infinity. But you grow it in a controlled way so that you keep the relative relationship between the number of samples and the size of it. So this high-dimensional model kind of analysis can be used a lot if you look at like covariance matrix estimation. But in this case, we look at the hypothesis testing problem. So let's look at what's already there in the literature. Let me plot this number of size alphabet according to how they grow with number of samples. Okay. So on the left-hand side is the Hoeffding setting, which basically number of size alphabet is actually fixed. In the middle is basically the size alphabet will grow linearly with number of samples. On the right-hand side is grow quadratically. And I'll explain why I stop here. Okay? But if you think of this regime, you have m size alphabet is m. A number of samples you accumulate per bin or per letter in the alphabet is actually will increase as number of samples increases. But in this case, it's a different case, because you're going to have a lot of symbols that you haven't observed in this case. Okay? So the first result by Panitsky showed that if there's no test that's actually asymptotic consistent beyond the quadratic growth. Okay? And if you look at anywhere here, there's a test that's actually asymptotic consistent. So probably a false alarm misdirection decrease to 0. Okay. And you can look at central limit analysis. The first result by Wilkes that basically shows that if you look at a test statistics, it will be asymptotic chi-square distributed with the degree of freedom actually linear in the size of alphabet. Therefore, you have larger degree of freedom, which is larger size of alphabet. This distribution will become more flat. Then you have larger probability error. And if the same analysis can be done for sublinear growth or above sublinear growth or above linear growth. And one interesting result by Ermakov in 1908 is actually he can show that the chi-square test is actually optimal in the central limit theorem analysis. Okay. And Hoeffding test, as I told before, works on fixed m, and you look at exponent, and we know that exponent doesn't tell a good picture of what's actually happening with large m. And Barron showed that the linear growth is actually critical in the sense that there's a test with non-zero exponent up to this point. Okay, so you can increase m, grow that simultaneously with number of samples. As long as that doesn't grow faster than number of samples, then you have a test that has non-zero exponent. But going beyond that, he shows that no test has non-zero exponent. And our work is actually in this regime. How do you do large deviation analysis in this part?
Could you give some motivation? Something might not be clear about it. A situation where you let the number of samples, the alphabet size grow down. Just to
right. So one way is we have that actually from theoretical analysis, try to understand how the number of samples and alphabet play with each other. The other is if you start with a test problem, Gouin's fit test problem, that has real value observations. Okay, you want to make a test. So one way to do it is you quantize the observation first into a finite number of bins. And as you accumulate more and more samples, if you have finite bins, so let's think about what bin means. So if you have 2 bins, so within the bin, the difference between the alternative distribution and the null distribution will not be seen because you glue them together, right? So if you have more bins, means your test is going to be distinguished, more sensitive to difference between the alternative and the null hypothesis. Okay? Therefore, if you have a number of samples that's growing, one way to naturally use this is grow the number of bins simultaneously. Okay? And you can either grow it slower in number of samples, but in some cases, actually beneficial to grow it faster than the number of samples. And actually, this two were actually motivated by this application. Okay, so let me. I was saying this work will focus on this regime, and that's basically you have a number of samples grows slower than the size alphabet. On the other hand, size alphabet is subquadratic in number of samples. Okay? There's no test that's asymptotically consistent beyond this point. And recall our classical exponent. What it looks like, is basically you look at log of probably false alarm and normalize the number of samples, and that's your definition of exponent. But the background showed that for any test you can look at, this value is 0. The reason that I put a minimum of this because you can always say you just always decide in favor of null hypothesis. Then you can make this false alarm to be infinity, right? So it makes sense to look at minimum between these two. And actually, that's the exponent for the product of error. Okay, so background result basically showed that for any test, this product of error will decrease to 0 slower than exponential in n. And therefore, if you look at large deviation analysis, because you need to pick a probability scaling here, n is not the probability one in this region. Okay. And our question is, let's define the exponent in a different way. We still look at log of probability false alarm, but look at different normalization, a different scaling. Okay? And the question is, what's the right scaling here? Okay? Remember, in the previous exponent, it was n here, but we know that in this case, it doesn't work. Okay? And when we say it's appropriate, we mean two things. The first, the exponent defined, general exponent defined this way has to be finite for any test. If it's infinite, that means you cannot distinguish different tests. The other is they have to be non-zero, right? Otherwise, your scaling is just too large. So let's go back to this picture. We know on the left-hand side, the traditional exponent defined with a scaling of n. On the right-hand side, we want to know what's the right scaling. And if you make a guess, what you can put here. Okay, and our answer to this goodness of fit problem is that you put this number, this function, in the scaling part. And if you compare these two definitions of exponent, let's look at what's happening when m is equal to n. Actually, this number will become n, right? So it's sort of continuous from here to there. Another thing is you look at this part. See, this term will not increase to infinity once you go beyond or in quadratic of n. Okay? So that's actually consistent from what we know before. And this definition is holds for anywhere that's superlinear in n and subquadratic in n square in n. Okay. So let's stick to this generalized exponent definition. So you normalize the log of the false alarm by n squared divided by m. Okay? And let me back up the story why this is appropriate. So I said, first you need to look at have achievability result. This shows that there exists a test such that this general exponent is non-zero. What this means, so if you pick really large normalization that's faster than n squared divided by m, then your exponent will be 0. Okay. And in our case, we are saying your scaling is not too large. Okay. And we also have to show it's not too small. And the other result we can show is converse. It's basically for any test you can think of, the generalized exponent defined using this normalization is upper bounded by the finite number. Okay. So our scaling is not too small. So that's our justification that this decreases with normalizations n squared divided by m. And okay, I'll talk with intuition why that's the case in the next two slides. So let me give you more. So we have bounds here, but what that depicts in geometry, in picture, is you have two quantities, which is generalized exponent of false alarm and misdetection. Okay, and there's a trade-off between these two because you can change the threshold. Okay, and we have two bounds. We have upper bound, which is here, that says this regime is not achievable for any test. Of course, you want as JF and JM as large as possible. Okay? But we show that this is not achievable. And then we have a matching lower bound that actually match the upper bound, says anywhere here that's achievable some test. So therefore, we have a result that's not just tight in terms of scaling, but you also have a tight result on rate. And this optimum test achieve this upper bound is one interesting thing called coincidence-based test. Okay, so let's go into that. What that means? It was proposed by Paninsky, and he looked at the test statistics. So okay, let me give you a definition here. So this is the empirical distribution. So the number of symbols that appears, the number of times that J symbol appears. Okay, and this is basically the number of times the J symbol appears is 1. Okay, and the test statistics basically counts the number of symbols that appear in exactly once. Okay, remember we are in the sparse sample regime, where the number of samples is growing slower than the size of the alphabet. And
is gamma going to come up a lot? Because maybe we should put a gamma whiteboard.
Oh, okay.
Yeah, I think it does come up a lot. So just make sure that that's built in.
Thanks. So if you define, can you see it here? Okay. So this is basically, if you look at, it's normalized by n. Or n, with basically number of times that zi is equal to j. Okay. So let's look at the I symbol, and if the I symbol is actually the I sample is actually you see symbol j, then you count 1, and this is basically empirical distribution. Okay. So the frequency that j symbol appears. Or if you're familiar with histogram, that's basically histogram. Okay. And you can show that actually if you look at the coincidence-based test, the statistics is largest under a uniform distribution. Okay. So then you can compare this coincidence-based test to a threshold. And remember, because it's largest under a uniform distribution, then you should see whether it's smaller than the certain threshold. Okay, that decides in favor of the alternative. Okay. So why you look at number of symbols appear exactly once? That's because if you look at a sparse sample regime, because the number of observations is much smaller than the size of the alphabet, then the histogram, if you see it, is actually most times sparse and it's shallow. So most of symbols doesn't appear at all. You see some symbol appears once, some symbol appears twice. And it's unlikely for a symbol to appear more than twice. That's another simulation example we can see. So that's why you can capture this, but just look at number of symbols appears exactly once. And if you look at the performance of this test, so we can characterize it completely that the exponent for the coincidence-based test, you have basically, if you're familiar with large deviation, this is basically variational, or the Laplace transform, the transform of the log moment generating function. And you can calculate the value explicitly. And this will be bigger than 0 for any tau in this set. I guess I shouldn't throw this big formula here. But let's look at how they compare to the numerical experiment. So again, here on the x-axis, I'm looking at, remember our scaling is n squared divided by m, so I'm looking at n squared divided by m here. And the y-axis is probability of error, so false alarm or misdetection. And it's probably in the log scale. Okay. And if you look at generalized exponent, it gives you a linear prediction. It basically say that the error will decay, the slope will be, give you an estimate of slope. So the probably error will decay linearly when you look at log scale. And the blue one and the green one are actually from numerical simulation.
You chose the threshold to get the same.
So we chose the threshold so that these two curves get similar slopes. Okay. I guess okay. For this case, actually, the way we choose the threshold, remember, we have this result, that if your threshold is chosen this way, you have a certain exponent. And that's how we chose threshold, and you have this two curve. And you can see that a general exponent will give a fairly good approximation to the slope. The difference between the theoretical prediction and what you get in experiment is due to two reasons. First, we're not choosing the threshold wisely enough so that this will cancel out. But the other is you have higher order approximations that's hidden in asymptotic analysis. Okay. And if you look at another picture, this part we do the choice of threshold better, and you can see the exponent approximates slope really well. Okay. So if you contrast this with what you get from Hoeffding test, remember in the Hoeffding test, if you have larger alphabet size, then you have a poor approximation to the positive error. But in this case, we're able to capture how the error decays.
What was the difference between the previous slide and this one?
So this has different epsilon, the different distance between alternative and the null distribution. Okay. Questions so far? Okay. Right. So let me come to a more classical test, which is proposed by Pearson. Okay, this is a picture of Pearson. And he studied this probably more than 100 years ago, and it's really widely used test. Okay. And what it does is really simple. So you basically look at a weighted L2 norm between the empirical distribution and the null distribution. Okay. So this is the number of times the J symbol appears, and this is the null distribution, and you weight by the pi j again. And you look at L2 weighted norm of that. And if you compare that test statistical threshold, that gives you the Pearson test. Okay? So if your distribution is different pi, you're going to have a non-zero weighted norm. Right? And if you analyze the Pearson's test using asymptotic consistency, we know it's actually consistent. Okay? So probably the false alarm misdetection will decrease to 0. But if you look at this in the mirror of large deviation analysis, we can show this actually far from optimal. Okay, so for this classical test, so for any choice of threshold, you can show that if you choose a threshold so that the general exponent of misdetection is bigger than 0, then you can show that this Pearson test has 0 general exponent of false alarm. So what I mean by that is if you compare that to the coincidence-based test, you can make them so that the probability of error of misdetection will decrease same way, but for the Pearson test, you're going to have larger probability of a false alarm. Okay? And you can look at the geometry picture I put up. So okay, this is the null distribution pi. Okay, think about this in this is a probability space. Okay, collection of probability distributions. And remember, our Pearson's chi-square test is basically weighted L2 norm. So this is the ball of the Pearson's chi-square test. Okay, so if you see an empirical distribution that's inside the ball, you decide in favor of the null distribution, the null hypothesis. If it's outside of ball, it's H1. Okay, and this star shape, which is not actual depiction of the decision region of the coincidence test, but I choose star because it's non-convex. So let's think of this as the decision region for the coincidence test. So anywhere when empirical distribution falls here, you decide in favor of null distribution, and outside is alternative. So we can compare these two tests. Actually, you see if you choose threshold so that they have the similar probability of misdetection, exponent of misdetection, then chi-square test will have smaller region that decide in favor of null hypothesis. And there is some place in here that achieve achieve 0 generalized exponent. So what that event actually is, so although this is a small probability event, that a certain symbol appears more than twice. But if you look at how frequently this event happens, actually that event doesn't decrease that fast. Remember, our general exponent here will decay at n squared divided by m, But this event will decay slower than that. Okay? Therefore, somewhere in the decision region, when the number of symbols appear too many times, this region is where hurts the performance of Pearson's chi-square test. Any questions here?
Well, the connection with the diagram. So that set A is.
So that set A will be somewhere in here. So if you go from pi, you see the probability that pi actually deviates to someplace here. That event, the probability of that event, doesn't decay as fast as enough, as what the general exponent tells you. Okay? So what we can say here is the Pearson chi-square is far from optimal. And because you see that the event that hurts Pearson chi-square test is a certain symbol appears too many times. I remember in the test statistics, you basically take the quadratic of the number of symbols appears. Okay? So one way to improve it is to look at truncation of the statistics. Okay, so let's go to the next story. Remember, in our previous case, we look at uniform null distribution. Okay. We always assume it's uniform. But what about what we can do for the non-uniform case? So actually, if you look at analysis, there's a simple way to motivate how you can design a test for the non-uniform case. Remember, in the sparse sample case, most of the symbols will appear 0 times, once, or twice. So let's just take those 3 terms. And what we can do is put different weighting on these terms. And one way to think of how to choose the weighting is to see whether the weighted term will have a asymptotic approximation to L2 norm, which is similar to Pearson's chi-square test. And that's the weight you can put in there. Okay. And if you look at the expectation of this test statistics, you'll be similar to the L2 norm between the alternative and the null distribution. Okay. And we can show that for this test, this has a non-zero generalized exponent. So, any questions up here? Okay. So that's the story for the goodness of fit problem. I have plenty of time for. Okay. So we can apply this tool to a different problem. Remember, we have the composite versus composite case. So we can apply this tool to a binary classification problem. So this problem says, let's say you have alphabet of size m, and you have certain training samples. You have 2 sequences. One sequence has distribution pi, okay, and the other sequence has a distribution mu. And this pi and mu are not known to you. You want to learn it from the training samples. And then you're given a test sample, which has a distribution mu, and your task is to decide whether it's equal to pi or it's equal to mu. Here with the formulation of the problem. So our goal is to we can use the general exponent tool to analyze the problem as well. So one question we can ask is, let's say the pi and mu both spawn a size alphabet m. If m grows simultaneous with the number of samples, okay, basically you look at a very sparse sample case. That happens when you look at text classification. There's a symbols appears less frequently. And how fast can m grow, or how many samples, training sample or test sample you need, so that you have a asymptotic consistent test. Okay, so your probability of error will decrease to 0. And so a given test will decide in terms of looking at those 3 observations and decide either it's 0 and 1. And the asymptotic consistent result, you can characterize that using general exponent. So what I'm plotting here is on the x-axis is number of training samples. Okay. On the y-axis, there's number of test samples. Remember, we have training here and test here. The question we want to answer is, in what regime the test is asymptotic consistent. Okay. And if you apply general exponent tool, you can get two curves. The first curve saying, this is number of training next time test samples. If they have certain trade-off between these two. So if your number of size alphabet will grow smaller than the number of test samples times number of training samples, that gives you this curve. Anywhere here, you're good with the classification problem. You can achieve asymptotic consistency. The other curve is given by n squared. And so if you put these two results together, basically you can say that if your test and training samples is in this regime, which is basically size alpha is quadratic in the number of training samples, then you have a test that's actually asymptotic consistent. Okay. How many times do I have? I guess I go too fast for the talk. That's clear with this result. Okay, so if you look at this result here, what this is saying, so think of you have a training sample, test samples, okay? So your problem is first ultimately constrained by the number of training samples. If you have certain training samples, no matter how you grow the number of test samples, once number of test samples is larger than the training samples, it doesn't help at all. Okay? Actually, this is consistent with one of early analysis in the large sample case instead of sparse sample case, is that your test samples, if they grow faster than training samples, it doesn't help. And the n squared is very similar to what we see before for the Green's fit problem. Okay. And okay, so we see a lot of normalization of n squared divided by m here. And I think I have time to give a story why that's the case. Okay. So that's actually comes from birthday problem. So the birthday problem basically asks, let's say if the person's birthday will be uniformly distributed over the whole year, okay? And how many people there has been in the room so that there's at least 2 people have the same birthday. Okay? So if you look at our problem here, this picture here. Okay, so it's basically this is basically the kind of birthday you can take. Okay, and you want to ask how many samples you need, or what's the number of births you can choose, so that you have at least 2 people with the same birthday. Okay, and that answer is quite simple. So let's say you have m birthdays. 1 equal to or 366 here. And the answer here, if you see the results, let me see. There's normalization here. Okay, you can make a good guess what's here. That's basically square root of m. I'm not fast enough to give a number here, but
18, 19, that sounds good.
So that's actually the basic tool you can analyze tests in a sparse sample case. So whenever you try to prove something in terms of converse, it's basically the same intuition here. So how many samples you need so that you have at least 2 people that have on the same birthday. So why that's the case is because if you look at the empirical distribution, okay, if all symbols appear just once or 0 times, there's no way you can distinguish 2 distribution. Only you see something that's rather than 1 and twice, or 0 and 1 times, you can make a claim. Okay? And that's how you can prove this result in the converse case. In the achievability, you need to use the highway tool from large deviation. So let me summarize my talk.
None of us have a same birthday.
Really? Well, we don't have enough people though, so but we can quantize it. Okay, count the number of people in the same month. Okay, I guess that'll help. Okay, so let me summarize it out. So first, I show you that if you look at Hoeffding test, we know the classical exponent is not suitable for sparse sample problems. Okay, you have the approximate really poor when you have large alphabet. And then we go through, we see there's a new definition of a general exponent. So for other problems you look at, you need to look for other normalization. That might not be this case. Okay? But you can make a pretty good guess if you have similar intuition there. Okay? And it gives a fairly good approximation to the slope. Okay? And if you look at, you can look at larger. So this is asymptotically basically the first order term. If you look at mode term, you can approximate this error better. Okay? So you can look at Bahadur type of analysis there. And there's more problem that's of similar kind. One is testing whether two distributions that you do not know how close they are. Okay, that has application in anomaly detection. So for example, so if you try to sample a certain environment, okay, and in one part of that environment is wrong, so that distribution is different from the other part. Okay? So you can apply a test of testing the closeness of two distributions there to sample every place and see which one distribution is different from the others. Okay? And that has application in anomaly detection. And one important thing we miss in the talk that we haven't solved is how do you bring geometry in this picture. So if you look at classification problems, except text classification, mostly image classification, the major tool like SVM, they rely heavily on the geometry, underlying geometry on the picture. Okay? But here we are restricting ourselves to a finite alphabet. And we hope that someday we can bring the geometry in the picture.
Could you do us a favor?
Yes?
Could you show the beautiful geometry for just the simple versus simple?
Oh.
You know, it's too pretty to leave out.
Okay.
Just simple versus simple. Classical.
Actually, that's.
When kids went to elementary school, they learned universal.
Well, that's actually the picture that attracts me to hypothesis testing. Okay, so let's look at the probability space. Okay, so basically set of probability distributions if you look at the finite alphabet. So let's just say this is one distribution. So let me go back to the initial picture here. Okay, so let's look at this case where you have only two distributions, right? You know them clearly. And I guess let me draw here. So if you look at in the probability space, so pi is one distribution I'm drawing here, and mu is the other distribution. Okay, and if you want to look at what's likelihood ratio test, it's basically written as log of. One way to written is basically log of mu, and look at the empirical distribution. So you look at inner product between the empirical distribution and the likelihood ratio function. Okay, so it's a linear function, so that's actually a straight line here.
Yes, that's bigger than tau.
That's if that's bigger than tau, then you decide in favor of pi. Okay, so in probability space is actually the straight line. Okay, so that's a likelihood ratio test, and you know that's optimal. And I talked about the goodness of fit problem. There's a Hoeffding test, and if you look at Hoeffding geometry, actually what it does is, because it's general exponent, right? So it's multiple likelihood ratio. So it becomes, you approximate, you basically have an intersection of lots of hyperplanes, okay? And if you have draw enough hyperplanes, it becomes a ball. And this is KL divergence ball there, between a certain distribution mu pi. Okay. And the large deviation rate that I show in my talk from the Hoeffding test, the rate is actually basically the KL divergence from here to here. So that's for the large deviation analysis for the testing problem, it has a very beautiful geometry. And if you like to talk more, we can
Well, what is the difference between CLT and large deviation?
Okay. So so in this case, there's actually. Let me first talk generally about on CLT. So let's look at the sequence IID sequence. Okay. Let's say first look at law of large number. because you're familiar with. So you know from large number that you have a certain condition for its IID sequence with finite variance. Then you can show that this will converge to expectation. Okay, but if you look at the probability that you want to see what's the probability of the normalized summation bigger than a certain threshold. Or I can basically change it, put okay. So if you let's say look at Gaussian, right? So basically you're looking at threshold that closer to the expectation, and let's say this is zero mean. Okay, so this is what you can get here is from central limit theorem analysis. But for large deviation, you look at this threshold is string from zero, right? For large deviation, what you look at is bigger than the fixed threshold. Okay. So the difference between central limit theorem and large deviation analysis is one thing is look at that's what's happening close to the expectation. The other is look at tails. Yeah. But in this problem, when I say large deviation, there's central limit theorem. There's one additional assumption there. Is remember, our goodness of fit is all distribution that's epsilon away from pi, right? In central limit theorem, basically they are shrinking the ball here, so that this is shrink with 1 over either a size alphabet or number of samples, depends on how you look at the problem. Okay. Answer questions? Okay. Thanks. Any question?
Can you go to your last slide?
Okay.
You have a very nice region. Yeah, thank you. So can we conclude that if I have a fixed number of samples to play with, like some of them I have used for training, the other I have used for testing, I would do the square root m operator at that.
For fixed samples, it really depends on how many samples you have. But basic intuition is you do not want to play this to basically same. That's intuition getting from here, somewhere here.
The square root of m, 2 times square root of m is actually smaller than m, right? I mean, if m is bigger.
Well,
so if I have a fixed number of samples to play with, I have to use a certain portion of it for training and a certain portion of it for testing.
Yep.
I would operate. It seems that I would operate via the square root m rather than the m.
M is the size alphabet. Yeah. Yeah. And you basically want also you know that if you have the certain budget of if you can divide it into test and training samples. Of course, it depends on the problem, but most likely you want to try the case where you divide them evenly, see how that works. I mean, there's of course assumption made in analysis. But. Other questions?
Oh, thank you.
Okay. Thank you.